I would like to greet all the participants of the conference. And okay, I'm just giving this talk from my home back. Um, and this, as it has happened in many times in the last couple of years, I will just speak about cigarette sharing as well. So here is the title. This is multipartite cigarette sharing. And in this case, it will maybe it will be a little bit different, so that I'm just trying to be quite interesting. So here is the content. First, just overlook that what the cigarette sharing, what are the problem, what we were just handling. And after that, there's some more definitions and presentations, and hopefully at the end I will just show you some interesting things as well. So what is multipartite cigarette sharing distinguished it from the ordinary cigarette sharing is the participants are partitioned into different groups, which sometimes you can think that they are different departments and okay, they should be disjoint. And the membership in a qualified set depends only on the group and not on the particular member. So that it also means that any member from any particular department can be replaced by any other member from the same department without affecting that whether the group is qualified or not. So these settings is interesting only if there are a few groups and lots of people in each of the groups. Otherwise, if there is only a single people in each of the group, that it is exactly the same thing as the original secret sharing. So in these settings, very many unsolved problems. Even in groups, we have only two groups, many unsolved problems, which might be interesting. And okay, this we will see them later. So some of the definitions. So that first, an access structure, as usual, this is the collection of all of those sets which are eligible to recover the secret. Subsets which are of participants which are not in the access structure, they are all the information must be independent of the secret. The complexity of such scheme or such an access structure is the minimal load any participants must have. And it is well known that this minimal load is at least one, at least as much as the size of the secret. And structures in which this minimum is attained, they are called ideal structures. And those are long-standing open problem to give some characterization of ideal structures. There is a relaxation of the property. This is which we are called kappa ideal structures, in which the entropy method, which might give a lower bound on the complexity of the structure, it gives the lower bound exactly one. So that an ideal structure is necessarily kappa ideal structure as well. But the implication on the other direction doesn't hold, so that there are kappa ideal structures which are known not to be ideal. Okay, so that okay, so there is a gap between the two things, and it is also a very interesting question that how to recognize ideal structures, which are kappa ideal structures, which are not ideal ones. The kappa ideal structures are interesting because of very fundamental theorem of Brickel and Diven from 91, which says that these kappa ideal structures are actually very strongly connected to matroids. In fact, such structures are the so-called matroid ports. And so in a certain sense, each kappa ideal structures are in a one-to-one correspondence with all of the matroids. So each matroid gives rise to such a kappa ideal structure and vice versa. Okay, so what about multipartite kappa ideal structures? And here is the theorem of myself, Ferro Matus, and Carles Padró, that multipartite kappa ideal structures are the same as the so-called capped structures. So for when there is only a single group, then it is exactly the same thing as a threshold structure, so that qualified subset are all subset which have T or more members, and T and less than T members are unqualified. This theorem also just gives a recipe to generate or recognize all multipartite copied structures, so that how they can be generated can be made. And in the special cases of 1, 2, or 3 departments, it also just gives all the ideal structures quite interestingly, so that in this case we have a method for recognizing each tripartite ideal structures, so that we have a way to analyze them. For 4 groups, it is the equivalence is not true, so that for 4 groups there is a copied structure which is not ideal, and however it is still okay. So this is still a big question, that at least for 4, what some extra things can be just said about those structures. So the question, what the capped structures are. So here are the cap, and the cap structures are defined as each group, if subset of the groups have a cap, which tells that this subset of the groups has no more valid counts than what cap they have. So this is, I try to just read the power of the coalition of all departments in the subgroup. Subset A has, it is limited by the FA count, so that no more than FA people are simply just count from the coalition of the departments. So here is an example. We have 2 departments, and the cap for the first department is A, the cap for the second department is B, and the cap for both the departments is for C. And here, what you see here, it is that whenever this cap is not reached, so that this is A for the first department, so that this is the part when the first department it is worth to just add more and more people from that department, and adding more than 8 people from the department, it simply doesn't count. It will just cut. For the second department, the cap B is, so that in this case, also we have for the second department no more than people than what is indicated in the green. And as for the 2 departments together, the cap is C, so that they all together, if the 2 departments have more than C people, then it is exactly the same thing as if they would have exactly C members altogether. So what does it mean that a certain number of people from each department comes together, and whenever we are saying that this set of the participants, they are hitting a certain cap C, so that here is the cap C, whatever we see here, and the question is that when this cap will be hit. So we know that the first department, the cap for the first department on A. So therefore, to hit the cap C, that at least C minus A members should be from the group 2. Otherwise, as many people can come from department 1, there is no way to hit the cap C. Okay, you see, so that the total cap for 1 is A, so that here there can be no point can be here, so that at least C minus A people should come from the department 2. Similarly, there must be at least C minus B members should come from the department 1. Otherwise, there is no way to hit the group. And finally, that we should have to have at least C members from the both groups. So that this blue region, it simply just shows that which are those pairs of how many people from one department, how many people from the second department should come so that they would hit the cap C. If the number of the people they are from this white region, then there is no way they would just hit the cap C. Okay, that simply means that hitting the cap C, so that whenever you are just adding up, then this cap C, it will be just a valid cap for just determining that the power of the whole group. Okay, so that here we have this cap function, and for each disjoint, each subgroup of subset of the groups, we have this cap function, which is the FA, and this cap function, it must satisfy certain properties, namely it is for the empty set it should be 0, it should be a positive integer otherwise, and it should be monotonic, so that the cap for a larger coalition, it should be definitely cannot be smaller than the cap for a smaller coalition. Otherwise, there is no way to hit the cap for the union. And also, this cap function, it also must be a submodular function for the same reason, so that this inequality should hold. If this doesn't hold, then if the F A for A, B, and the A intersection B, this cap is simply just hit, then there is no way to hit the cap for the union if this inequality does not hold. So that at least the cap function must satisfy these 1, 2, 3 properties. So what are the capped structures? So in the capped structures, we have a collection of the participants, which are just in M groups. We have the cap function, which simply just gives the cap for each possible coalition of the groups, so that this FA is defined on the subset of the groups and not on the subset of the participants. And beyond that, we also have upward closed collection of a subset of the groups. This simply upward simply means that if one subset is an extension of any of the subset which is enlisted in A, then this extension must also be an element here, so that it is going upwards. So that this is the upward collection of the group subsets. And capped access structure is simply consists of those subset of participants, so that there are certain coalition, so certain set of the participants is qualified if and only if this coalition or this subset of participants is simply just hit the cap of one of the subsets in this collection script A. So once again, so in a capped access structure, the qualified subsets are those subsets of the participants which hit one of the caps of one of the elements here, 1A, 1A2, and so on, 1A3, so that in this collection. So that is the capped structure. Okay, so let's see an example for the bipartite and at least for the tripartite case. So okay, we have only 3 possible subsets of 1 and 2, so the 1, 2, and the 1, 2, and upward collection is we have 4, 1. This is the 1, 2, the 1 and 1, 2, 2 and 1, 2, and 1, 2 and 1, 2. Okay, so let's see. So this is in this case we have exactly the possibilities when the cap for the coalition 1, 2 is hit, and so that we have seen it that this is hit exactly for this part of the number of the participants from the first department and from the second department, so that this denotes this gray part denotes the qualified subsets. Okay, so let's go here. So that in this case, our subset will be qualified if they hit the cap for the group 1, or they hit the cap for the coalition 1, 2. So that they hit the cap for 1, it means that the cap for 1 is A, so that if the first department has A or more members, then they hit the cap for the 1, and they hit the cap for 1, 2, just in the previous case, so that the qualified subsets are in this case, these are exactly the ones which are just indicated here. Very similarly, whenever I have 2 and 1, 2, then they have to hit the cap for the group 2 and or hit the cap for the group 1, 2. And in this case, there are at least B members from the cap 2, or they are just here, which is just we have discussed before. And the last case, whenever they are hitting the cap for the group 1, they are hitting the cap for the group 2, or they are hitting the cap for the group, the subset 1, 2. And in this case, the qualified subsets are exactly those things which are just indicated here. So whatever this theorem says, that if you are just looking for the ideal structures, ideal bipartite structures, then they are exactly these 4 types, and there are no more. And what's more, than they are also ideal, so that they actually they can be realized as an ideal structures for 1 and 2. So what about for 3 dimensions? Okay, in 3 dimensions, we have 7 possible coalitions, and for each one, we have a cap value, so that this means we have 7 different values. And in this picture, I try to just show that at least how the caps they look like. There is only just one missing thing here, which is the black triangle, which tries to show that the cap F1, 2, 3, which would simply just chop down this small tetrahedron from the very thing. For the collection A, we have numerous possibilities. It should be just upward closed, so that if it contains 1, then it must contain everything which is just above 1, so that with 1 it must contain 1, 2, 1, 3, and 1, 2, 3, or it might contain 1, 2, and 1, 3, and 1, 2, 3, and that's it. So that this 3 is also a possibility, and so on. So that there are many others. Okay, so that let me show you. This is the same body, whichever I just made previously. And so that this simply just tries to show the different caps, so that here is the one, which is just an extra thing, which can be just that. So that in this case, everything is just positive. And I have another fantastic picture. This is much better. In this case, the tetrahedron here is simply just has been chopped down, but in this case there are nothing. Okay, they're nothing chopped up from the tops on the 3 corners, as it had been just chopped down in the other case. And so that this is another possibility for the cap functions, whatever you can just see. So that this is 3-dimensional caps here. Okay, so that is how the cap functions look like for 1, 2, and 3. Okay, so that at least we have here, so that I'd like to just give you at least some impression of one of the how the proof goes, and also a little bit correction for the definitions, whatever has been just made before, so that everything is almost the same thing, but there needs to be some slight changes and refinements in almost everywhere, so that things would just work as they should. So that at least 2 things. So the first, how this theorem about the statement that multipartite copper ideal structures are exactly the ones which is the kept structures. So that okay, that's here is the main points of the proof. So the first, every couple. So let's look at the copper ideal multipartite structure, which is the partition pi. So that this is simply just gives the partition here. This is in particular, this is a couple ideal um, secret sharing. And by the Brickell-Davenport theorem, couple ideal structures, they have a one-to-one correspondent with certain matroids. So that in this case, this is a couple ideal multipartite structure. So we have a matroid which is associated with the structure. So let this matroid be this M. Then this matroid can be this matroid, it also just satisfies all the symmetries what this couple ideal structure did, so that we can take we can factorize this matroid M by this partition. So simply just take collide all the big parts, and so that we are just getting another structure. This factorized structure is a polymatroid. It is not a matroid anymore. However, it has an integer values as it is inherited from the M, and this is a polymatroid on the groups. Well, and the groups are from the partition, so that it is defined in the subsets or subsets of the groups of the partitions. And actually, the ranks of this polymatroid, they will define the caps value, so that it is exactly the f function f what is defines the cap values. The matroid M, it can be recovered from this factor matroid uniquely, and this is due to the certain symmetries what you have. Next, we are just looking at the secret itself. So that the secret, it defines a one-point matroidal extension of this M, and also it is a one-point extension of this factor polymatroid N. And the secret, it has rank 1. And the qualified subsets are exactly those subsets whose rank is not increased by this extension. This simply means that the qualified subset, they recover the secret, and so therefore the rank will just remain the same thing. The rank of the unqualified subset adjoining the secret should increase by 1. This is simply just a translation that unqualified subsets are independent of the secret. So, okay, the next thing is just simply looking at the one-point extensions of a matroid, or in particular, this polymatroid N. And this one-point extension is uniquely characterized by the so-called matroid, the modular cut, whatever this modular cut is. And this is a modular cut in the factor polymatroid N. And actually, this modular cut is simply just the collection of all flats whose ranks simply do not increase. And this modular cut is simply just corresponds to the collection A in the example, so that it should be just upward closed, but it is not only upward closed, but it should have to have certain further properties, which are just interesting or important if there are certain degeneracies in the rank function of the polymatroid. So the certain ranks, they are just agree, or which typically they do not do. And in this case, there are some more extra examples here. Okay. So the next point, which I'm just would like to tell you, is the another claim that the bipartite and tripartite couple ideal structures are actually linear, so that all those structures can be just realized, and so that they are actually ideal. And okay, so that for the bipartite, this is very similar. However, for Okay, for tripartite, it is more involved, and here is how exactly the things are just going. So that we are just looking for the polymetroid n first. This is an integer polymetroid, and it has three base elements, and all such polymetroids are simply just linearly representable. So that polymetroids, integer polymetroids on three elements, they are linearly representable, so that's no problem. The problem is that the 1-point extension of n, it also should be linear. And if it is linear, then the polymetroid, the metroid extension M, it is also a linear stuff. And this is due to the fact that the linear representation of this polymetroid, it can be arbitrarily large. And for the different participants, we can just get certain so-called generic elements of this extension, so that those elements, those are vectors which do not lie in any special intersection of the generating elements. So the next question is that the integer polymetroid, so that n plus the secret. So that this is integer polymetroid in 4 elements. So the n plus the secret. And whenever this such a polymetroid is linearly representable, if it is linearly representable, then m is linearly representable, so that we are just done. And any integer polymetroid in 4 elements is linearly representable if and only if it additionally satisfies the so-called Ingleton inequality. So that here is, I just wrote the Ingleton inequality as a linear combination of the ranks of certain subsets of the set A, B, C, D. So the question is that this n or with the extension of the secret is linearly representable or not. And so in this case, okay, so that we have an additional interesting property that this Ingleton value plus 2 times the Ingleton value plus the secret is at least, it is non-negative if S is any of A, B, C, or D. So that this is a general property of the singleton. And so therefore, if we have integer polymetroid n, and we have this one element extension by the secret, then this ing, this is an integer value, as you can just see from here. And if it's negative, then it is at least -2. This is the 2 times -2, but adding something and adding 1, it should be non-negative. So that the only possibility that this ing, it must be non-negative. So that this is the conclusion of the point. Okay, so that thank you very much. And so that's conclusion. This work has been done jointly by Ferro Matus and from Prague, and Carles Padro from Barcelona. And unfortunately, Ferro has passed away 2 years ago. Hopefully, he would just enjoy this thing. And also, finally, I would like to thank for all the organizers of the conference, the possibility simply just delivering this lecture, this offline, and also I would like wish everyone a very good and very pleasant conference, at least those who are just here. So bye bye, and okay, see you.